We will wait a little bit for participant if after joining for the participants. Okay.
Sure, sure.
Okay. Let us start. Otherwise,
Okay.
we will be late. Okay. So, good evening, everyone. It is my great honor to welcome an esteemed industrialist, come academician and researcher, Mr. Shuddha Sattva Ghosh, to session 7 of day 4 of our Auto Faculty Development Program on Semiconductors. He did his B in electronics from IIS Shibpur and MS in electrical engineering from University of Delaware, USA. He is currently based out of Netherlands where he is working with ASML, world leading manufacturer of photolithographic equipment. He has around 20 years of experience in product development related to optics, optoelectronics, sensors, and instrumentation that includes R&D organization, both academic and industrial. He is expertise in product development, related semiconductor manufacturing, medical instrumentation, mining, and atmospheric studies. So, don't wasting our time. We may start our session now. The platform of yours.
Thanks, Gautam. Thanks for the introduction. And thanks, everyone, for inviting me and joining this session. It's an honor also for me to be part of this faculty development program and at Abacus Institute of Engineering Management and share with you some of my experience and what I've learned also from my industrial journey overall. The topic of today, as I mentioned, as is semiconductor manufacturing, and with also photolithography because that's what I'm part of doing. And yeah, I wanted to share some of the things. Uh, so the agenda for today, I will start with a brief background on semiconductors overall and also the necessity or how critical the semiconductor manufacturing is. Followed by, I will give you an brief overview of the manufacturing process. I will touch upon also the industrial ecosystem for semiconductor design and manufacture because that's also very key in the modern world. Then I will go into the overview of the photolithography process, what it is and what it's all about, and its significance in the industrial semiconductor manufacturing industry. And I will also go a bit more details on some of the outlining some of the subsystems for photolithography equipment. Yeah, definitely on the ASML machines which we make. And then I will close the discussion with a summary and the future outlook. Because I would always like to have a more interactive session, but because of this online environment and also keeping in track of time, I would suggest to hold on to your questions till the end of my presentation, because then we can have more interactive session. Had it been a much more one on in-person thing, I would have welcome questions as I'm presenting. But during this environment, I think it's preferable if you can pause your questions till the end of my presentation. So yeah, so without further ado, I will start. So the first thing is semiconductor and its uses in the modern day life, everyday modern life. I think we are part of everyday, any normal person experience the utility of semiconductors, and starting from the time we wake up. Like, we have alarm clocks which we at home which wake us up, which are digital. More these days, we have instruments like, all the equipments which we use at home, the vacuum cleaners, the refrigerators, the washing machines. All these things have been made possible due to the home appliance, as we go on more and more, uh, possible due to the development of the semiconductor technology. Communication and entertainment. Yeah, I think the way we are communicating now, that has been possible due to the semiconductor technology, to say in brief. And yeah, we all know mobiles, they are, how versatile they are, both in providing entertainment and as communication devices. These days, it's not at your home itself. You can create an entertainment center, which has been made possible again due to the semiconductor technology, its improvement in overall progress over the years. Then, yeah, transportation. Uh, if you travel by car, the modern cars are more or less, it has more of, people say they have more electronics parts, and it is electronic than previously mechanical parts. And just to go back in time, few years back during the COVID period, you know, the supply of semiconductor chips was delayed because the restrictions in transportation, in the logistics, and the overall situation, and that actually delayed the production of cars. So that is how important the chip or the semiconductors has played a crucial role in the existing cars. Not to mention the modern cars which are coming of the future, the electrical vehicles, and also the unmanned cars which people are currently testing, and maybe in production, maybe in rollout for our daily life very soon. Medical instruments, starting from your home blood pressure measurement, or sugar measurement, to more complex equipment like the MRI scanners, the CT scanners, the X-rays, the the robotic surgeries. All these use equipments which uses the semiconductor chip at the very core, and it is because of these chips, the functionality which has been made these things possible. Illumination, yeah, the gone are the days where we had gas, lighting, or the coil heating place, which would for bulbs. It is all LEDs, and this is also uses semiconductors. It is heavily reliant on typical type of chemical, which helps in type of semiconductors, which helps in the illumination, and changing the illumination, make it more fancier and greater. And yeah, unfortunately, it has also its applications in not so good way in the defense. It has an immense impact on the defense technologies, the development of it, all the missiles, all the ICBMs, the fighter jets, the tanks, and everything which we see in the defense is heavily dependent on the semiconductor technology. So much so, the modern warfare is less of gun and shell and more of electronic warfare, where you can dominate the opponent because of your superiority in the electronics technology. And all of them uses semiconductors for their functionality. Just to give an idea how important is semiconductor in terms of, in 2024, the global semiconductor sales was around 630 billion USD, that's US dollars. And in 2025, it is projected to grow by to 700 billion USD. This is all projected, and yeah, so you can imagine how important the semiconductor market is become in our overall lives and globally. So when we talk about semiconductors or any instrument that use a semiconductor, the heart of it is what we call a chip. Now, what is this chip? It is It's a microchip. It's what we call it as a microchip, or a chip, or a computer chip, or an integrated circuit. Is basically a set of electronic circuits on a flat, small piece of semiconductor platform. And on this chip, the transistors act as miniature electrical switches that can be turned on and off depending on the conditions, the voltages, the how the potentials is defined on them. And this is how it functions. And if you look at the modern microchip, multiples of these billions transistors can fit in a very on a chip which is the size of a finger lane. And this is what is really crucial, that we can pack all this multiple numerous circuits on a single small area, which has improved its functionality and it has improved its capacity to do multiple functions, and it has made its usage felt in the modern life. Now, when we talk about chips, broadly speaking, industrial chips, there are a couple of broad divisions. One is the logic chip, which is typically the brain of any electronic devices. Basically, they are the processing, they process the information, which are, our microprocessors in computers or mobiles or laptops or anywhere. Then there are memory chips, which you use for storing the information. There are type of application specific chips, integrated circuit chips, which are called ASICs, which is a single purpose chips, which are very specific logics, and they've been custom made to perform this kind of applications. And then there are system on chips, which combines many chips and circuits on a single platform. And on the left side, the image is what you see here is basically, a typical chip which you can see in any PCBs or any of those instruments. And what all of these chips finally boil to is when we call about chips on a semiconductor, it's basically all these chips consist of the circuits and the transistors, which is created on a wafer and by adding and removing materials on a multi-layer lattice network. And on the right side, what you see is basically a scanning electron cross section of a chip. So as you can see that there are multiple circuits, there are gold aluminum deposits, there are trenches, and these are the things which actually function as circuits in a real world. And this helps you to get the functionality, the applications which we see on real world. It is these small circuits on the left bottom which enables the chip to behave as it is, as it's expected to behave. Now, what makes it possible? What is the significance of this? How it has impacted the modern life? On the left, what I show you is an image of the first computer which could do some electronic numerical computation. This is called the ENIAC computer, and in 1946 this was made. And what you see is this computer which was using the vacuum tubes, the controls and valves and those kind of things. It needed a room which is like 24 meters long, and it had 40 panels, and it weighted 20 tons, the overall, the platform. And what the same functionality, what modern chip technology has enabled is to put it in a single chip, which is like 7.44 by 5 millimeter in dimensions. And basically, it's the same functionality, and which was done in 1946. The same amount of computational power was enabled in 1997, and this is only on a chip. And it contains more than a lakh of 1,74,000 transistors on a zero point 0.5 micron. Each of this minimum dimension was 0.5 micrometers on a CMOS technology. So this is what has the modern semiconductor manufacturing and design has enabled the human civilization to be, shrinking a room full of panels to a very small chip, which can be, carried by a palm of a hand. So that is what has this semiconductor manufacturing has enabled people to do. Before we go further, we need to look into some of the milestones which has paved the way for the semiconductor revolution. The first thing we have to go for basically the invention of the point contact transistor by Bardeen and Brattain, which was in 1947. Then the invention of the junction transistor by Shockley. This was in 1948, and for them, all of three of them were received the Nobel Prize. Then came the demonstration of integrated circuit by Jack Kilby in 1958, and also the invention of MOSFET in 1959. And these were the basically the pioneers which paved the way for the modern semiconductor manufacturing and device design and manufacturing as we see in the modern world. One of the other guiding finders, which is really pioneering in the semiconductor field, is Moore's law. We speak it all and off. Now, what it says, basically, in 1965, Gordon Moore, who was then in Fairchild, I guess, if I remember correctly, and then he moved to Intel. He was the founding fathers of the Intel. He made a prediction that every year the number of transistors would double for the next 10 years. But he revised his quotation in his prediction in 10 years later. And then what he predicted was in 1975 that the number of circuits on a chip would double every 2 years. And this is an extrapolation based on the image trained, and the entire this forms the basis of the guidance of all the semiconductor design and manufacturing which we see around, which is happening which has happened in the past, and it's also going forward in the future. So based on this Moore's law, what we see is on the left-hand side is the number of transistors which the typical Intel processors have grown up over the years. From 1970, where you see few hundreds or thousands of circuits on a single Intel processor, to more than 10 billions of circuits, which you see by 2010. And this is a huge explosion over just over 40 years. And as we grow more, this goes on increasing. Unfortunately, I couldn't present the latest data. This is still 2010, but I can assure you that this extrapolation has continued and has impacts the overall manufacturing, semiconductor design, and even today. And it's expected to continue in the future. And when we are saying the number of transistors being packed into a single processor, what it means inside this, the dimension of the features of this, basically the dimensions of the transistors has shrunk over a period of time. And that's exactly what has happened. That when, back in the 1970s or 80s, when the micron was thought to be very small, to now where a single device or single minimum dimension that we have on a circuit is of the order of nanometers. And this is what has been achieved, and this is what has been predicted by Moore's law. And this forms the driving factor of all the design and the manufacturing of semiconductors, and also its application. Now, a mobile can do what a computer couldn't have done 20 years back, but a mobile is much more powerful. And it is this reduction in the semiconductor feature size, packing of more transistors on a single chip, that has enabled this revolution. Now, as we say, when we speak about the semiconductor manufacturing, there are some basic process steps that all chips has to undergo to have the desired, configuration which we want to have. So what are this? This slide I will go over briefly, schematic of all these process steps. So we start with a semiconductor wafer, which can be different size. Depending on typically industry, it's 300 millimeters wafers, but at lab level, it can be also a smaller size. So we start with that. We grow or deposit a thin layer of oxide or some materials, which is called by the deposition or layer work process. Then we cover the layer of the deposited layer with a very thin material called photoresist, which is by spinning. And what this photoresist is basically it's a chemical material. More so, in its texture, it's like the nail polish which women use, and it sticks to the surface. And it has a very interesting properties where it responds to light. Some of the photoresist, which we call the positive photoresist, when you shine light on it, it weakens the bond of the photoresist material. Whereas in others, when you shine the photoresist material, which is called negative photoresist, when light shines on it, it hardens. So what it once we cover the semiconductor wafer with the photoresist material, then we move to the next step, which is called photolithography. And what we essentially does is we shine the UV light. Typically, like UV ultraviolet light is shine on it, but with a caveat where we cover portions of the photoresist material with something what we call a photo mask, which is basically a glass window which has light and dark areas depending on where you want the light shine through and where you want to block the light. So basically, the photolithography essentially what it does is to allow or block the light based on our requirement. And once we do this process, then we go to the next process, which is called development and photoresist removal. What it does is basically, as you can see in the figure, that here we have exposed the portions of the light where in the other portions, the portions of the mask, photo mask, the light is not, these are not exposed. So basically what has happened is the portion of the photoresist which is exposed to UV light has weakened. It has, and in the next step with the development, this portion gets dissolved. And whereas the remaining portion, which were under the photo mask, which were not exposed to the UV light, they still remain as is. And this is a very critical step because it actually defines the area on which the subsequent process would happen in semiconductor processing. And then what we do is typically we go through the etching process, where etching is previously with we grow the deposited layer, but etching is just basically the reverse. It basically removes the material from the specified zone so that we can do further processing on this. For example, what can we do? We One of the things is we all know that any we can introduce some dopants, which are the the basic materials for how the semiconductor works. Like a p-n junction has p dopants and n dopants. So basically, through ion implantation or a doping process, we can inject specific ions on this exposed area and create a doped area within the semiconductor wafer. And so once the dopant is there, this is the result of the doping. And then we can repeat this processes, steps 2 to 4, which is like the same process from photoresist spinning to the basically the development and photoresist process, where we can actually deposit, this, and then we can do a metallization process where we deposit a metal and then again remove the process metals in certain selected areas by a process called liftoff. And this is what we see at the end, where we have a dopant area where on which we have a metal contact, which can which can be used to induce the electrical voltage or current, draw current from the circuit. So this is basically how a semiconductor chip, or how in a semiconductor chip the different circuits or different circuits or CMOS transistors are actually defined in a device level. And this is all the semiconductor manufacturing process uses these kind of process steps as we make the modern chips. Now here, basically, what this figure shows is basically as we have progressed over the design of the semiconductor processes, and the feature size has shrunk, from 90 nanometer to 46 nanometer to 22 nanometer. It has evolved. The overall one in design, the other in the manufacturing process. And by manufacturing, you mean people have explored different type of materials, different kind of dielectric materials, so that you can, because as we shrink the sizes of any device, what is the main problem is the leakage current. So basically, people have innovated different technologies to prevent that. They've also gone through different designs, like from MOSFET to CMOS to FinFETs. All this evolution has happened, and which has been enabled us to make chips which have where the devices are much more smaller, and it is the shrinkage is possible. And on the right side, what I show you is a typically what I did explain in the in my previous slide, a similar but a bit more elaborate on how the semiconductor, starting from the semiconductor wafer, what it does is we cut off semiconductor slices of semiconductor from a wafer from a, what we call a boule, which is basically you can say a column of semiconductor material which is grown by different processes, and from this we cut a slice of the semiconductor wafers for the which can be used in semiconductor manufacturing. Then when we polish this wafers, depending on the type, it can be both sided or single sided. Then we do a material deposition. Then we spin a photoresist. Then again we do a lithography process. And this process is kind of repeats depending on the how complex the semiconductor design is, how many layers are formed on the semiconductor layers, and depending on the complexity of the circuit, it can have a single chip can have more than 40 to 100 layers of these kind of intermittent circuits which are connected to each other. So, and also to make it happen, all this process steps has to happen so many times, like 40 to 100 times has to be repeated. And finally, once we are done, when we have the final integrated circuit to our liking, what it happens is we dice this wafer into small circuits, the chip, and then we package it into what we call the modern chip, and so that it can be protected. The packaging process ensures that the semiconductor circuits are protected from the environment or the shocks or everything what we see around us. Yeah, just to give you a scale of the microchip manufacturing, typical wafer size is 300 millimeter diameter. However, the thickness is very small, which is like of the order of 600 microns. So it becomes really fragile to handle it. It consists of 3D structures, which I mentioned, and which are also interconnected with each other. And there can be up to 100 layers built on this thickness of this wafer. And when we talk about the precision on which the precision scale on how the circuit should be layered, how it should be connected, and where which position it should be there, it's the order of nanometers. Just to think in terms of human comparison, a typical hair diameter is of 100 microns or 50 to 100 microns, whereas nanometer is much, much smaller than that. So it is quite, a wonder that we can make them at these days. So what it entails is the industrial process have complete automation. It cannot have any human interface when we make these processes. We need to use high precision equipment in both in manufacturing of these devices and inspection. We need high throughput, means number of wafers per hour. Like in industrial processes, time is money, and hence these equipments need to be really, really fast, and the processes need to be really, really fast also, but also accurate. And what we need also is a highly clean environment, because any small dust, even from human skin, flares or the hair, or even contact with the human skin, can damage this wafers permanently, which they cannot be used. So this is how how precise, how accurate this process has to be. Next, I will just go through the semiconductor ecosystem. This is basically the industrial ecosystem. And when we speak of the semiconductor ecosystem, first comes the chip IP core designer. So basically, these are the companies like IBM, Intel, AMD, Qualcomm, Broadcom, and these are quite unknown names in the modern world, because they actually design the chips and make it happen for us. Then there are also supporting them are the electronic design automation tool manufacturers, who actually provide the necessary tools to design these circuits. And they consist of companies like Synopsys, Cadence, Minton Graphics, ARM, to name a few. There are multitude more, but yeah, and newer ones are coming. Second is definitely, and it's not a hierarchy, but it's just how that's been shown. The second class is are basically the device manufacturers. These are the companies who actually make the device. In the past, we heard about Intel is Microns. These are in the past. IBM was also manufacturing, but over a period of time, they are phased out from that business. Now, when we talk about the device manufacturer, there's broadly speaking two types: integrated device manufacturers. These are the companies like Intel and Micron who design their own chips and also manufacture their own chips. And this has been quite gone. In the past, a lot of companies would do that. However, there's also a class of other chip manufacturers who are known as the chip foundries. The biggest name among them is TSMC and Samsung and these people. They're actually more like they don't design their own chips, but if somebody like Apple design the chips, they give it to these companies to manufacture the chips to the specifications. So they're specialized in chip manufacturing globally. And the companies like Samsung and TSMC, they are the largest chip manufacturers currently and the most advanced chip manufacturers in the world currently. Then then there are a branch of companies who supply the raw materials or like the silicon wafers, the photoresist, the photo masks, and they also form a very crucial part of this ecosystem. And because even like chemicals, like the water has to be a certain purity, and all the chemicals has to be a certain purity before it can be used for any device manufacturing process. So also the silicon wafers, the photoresist, the photo mask, and suppliers. And the companies, some of the companies here are Air Liquid and Shipley and multiple other companies who form the key uh, piece to the puzzle. And last but not the least, there is the semiconductor equipment manufacturers. These are the companies who supply Intel, the companies like the chip manufacturer, the actual equipment to manufacture this chips. And to name a few, ASML is one of the leaders of them. There are other companies called Lam Research, KLA Core, uh, Applied Materials, Hitachi, Canon, Nikon, and there are multiple more. But these are the leaders, the larger names which I'm telling about. And the semiconductor manufacturing equipment is not that well known in the Indian context, I would say, where the others are much more well known. But it's a thriving market because it is, as the chip manufacturing pushes on, so also these technological companies who make this, who work with the companies like Intel and TSMC to make that happen, to make that relevant chips. Just to give you a brief overview, in 2023, the market for this semiconductor equipment manufacturer was actually 110 billion USD. And in 2032, it is expected to grow by 270 billion US dollars. That's the scale of the industry which is growing. Now, when we talk about the semiconductor equipment manufacturer, I will just give a brief snapshot of some of the companies and their product lines. I'm not an expert in them, but I would always suggest all of you to go through their website and see what they do and the challenges they face. One of the leaders is Applied Materials. This company makes equipment for deposition techniques. There are different types of deposition techniques which is used, like physical vapor deposition, chemical vapor deposition, epitaxial vapor deposition, epitaxial growth, not vapor deposition. Then there are polishing processes which is needed. Then there are an implantation techniques, equipments which are needed also for dopant. There are also specialized in photo mask making, which is also a key niche skill. Second is lab research. They're actually also known for their deposition techniques, where they have atomic layer depositions. They also make etching equipments, wafer cleaning equipments, and photoresist stripping equipments. They're also involved in metrology. You will see that both applied and lab research have some common business line, but it quite happens. They have specialized. A company grows in certain level, and then they move to the other opportunities. Also, that's how it works. Even the last here is KLA Core, who are specialized in metrology equipment. Now, metrology forms a really big key part of the entire manufacturing process, because you can make everything, but metrology ensures that what you have made is actually metrology is actually what you needed, and the deviations. So basically, Keratin and code to make these equipments which can measure the dimensions of the patterns, the film thickness, layer-to-layer alignment, pattern placement, surface topography, and also electro-optic properties of semiconductor chip. And last but not the least, the photolithography equipment manufacturers. To name the few leaders, one is Nikon. Nikon is known. Both Nikon and Canon are they are into the semiconductor photolithography equipments. They are known for the camera business, but here in the semiconductor manufacturing business, they also play a key role. And ASML is also one of the leading manufacturers in photolithography equipments. This is an image of our setup in Veldhoven, uh, an area view of our factory. And it is the ASML actually stands for Advanced Semiconductors Material Lithography. It was an acronym which was developed in the past. Don't ask me why, but it is what it is. It was founded in 1984, and it is actually was a spin-off from Philips. It is headquartered in Veldhoven, Netherlands, but it has multiple locations worldwide, including USA and Asia, apart from Europe. It is the world leaders in photolithography equipment manufacturing, and they are engaged. We are engaged in active research, design, and manufacturing of both lithography and metrology equipments, but they are more known for the lithographic equipments. Now, I would start a bit more detailed on the photolithography process. Just we have briefly mentioned in the past, but now I will go a bit more different. So basically, as I mentioned here, the in photolithography, the wafers are covered with photoresist where they are spinning, and then we form a uniform layer of photoresist on a semiconductor wafer. Now, on top of that, what we use is a photo mask, which is basically a transparent material with some opaque portions on it, and this pattern of the photo mask is defined by what kind of pattern we want to, what should I say? We get what we want to achieve on the subsequent semiconductor wafer. And once we and at a high level, the photomask is placed on the semiconductor wafer, and through the photomask we expose UV light. And based on the areas, and a photomask has both transparent and opaque areas. And if it's a transparent area, the light goes through, and if you're considering a photoresist, it weakens the bond of the photoresist, and so that it can be later removed and dissolved. Whereas the areas on the photoresist which are not exposed, they can be hardened, and so that they can withstand the subsequent processes. What we have to remember that this photolithography is a very key process step for semiconductor manufacturing. And why is it so? Because it actually defines the minimum feature size on a device on a chip. Because on the area which is defined by a photolithography, the subsequent processes happens only in that only in that area which is being defined. So the smaller you can define the feature, the smaller your feature, you can control the process, and the smaller is the device which will become out of the processes. And when we speak of the range of the pattern on the size of the chip, it can range from few microns. In the past it was hundreds of microns, but currently it's few microns to few nanometers. And as mentioned, the hair diameter is 50. Human hair diameter is typically 50 microns. So this is how small these features has to be made. And as you can imagine, it's a really complex process that depends on the interaction with optics, the electrical, the mechanical slash mechatronic, and also the chemical properties of the photoresist. So this interplay makes the photolithography process a very critical process in the overall semiconductor manufacturing workflow. Uh, when we talk about photolithography, also there are types of okay. I thought sound, but okay, this is fine. There are first two types which I will address, which were the basis for the original photolithography equipments. One is the contact printing, and the other one is the proximity printing. So on the left side, we show the contact printing. Here, what we do is the photo mask is actually in direct contact with the photoresist. So basically, it's kind of builds. It's directly placed on top of the semiconductor wafer on which the photoresist is been layered, and the UV light passes through. And basically, this can produce quite high resolution patterns on the photomask. And they were the original, in the past, they were the original type of photolithography equipments that were made from based on these concepts. And the defining resolution is basically how smaller the on these ones was basically how smaller you can make the features on the mask. So basically, this contact printing was quite effective to sub-micron level to make features which were sub-micron level on a device. Then, but one of the main advantages, which is disadvantages of this one, is basically, as you can imagine, since the mask, the photoresist contact in the mask, after multiple reuses, it becomes, the yield goes down, and it also puts defects on the mask, which has to be clean, and it's a tedious process, not really useful process to be followed. So, as an upgrade of that, people came up with what we call the proximity printing. Here, the technology remains the same, but there is a slight air gap, like 20 to 40 microns, between the photoresist layer and the mask layer. So what it helps is it avoids a direct contact, and the mask can be reused multiple times. However, due to the optical effects, this resolution is not that high. It typically can range. It's still okay to reach resolutions of 2 to 4 micron, but that's not quite sufficient for the modern chips. The requirements of the modern chips. However, we need to understand that both this contact printing and proximity printing are still used quite heavily in lab level. They are not, though not suitable for the industrial scale. They are really large scale industrial processes. They're still well in use for lab level equipments. And yeah, I myself have started using contact printing when I was a graduate student. So these are still quite useful. Then the other variety is what we call the projection printing, and that is more what we current industrial. This forms the basic concept on which the current photolithography systems are all based on. Here, the photomask is slightly can be put a longer distance away from the semiconductor wafer with the photoresist on, and the image and what you have is a bunch of optical systems like lenses, combination of lens, mirrors, or both, which can image the pattern on the photomask onto the photoresist. So basically, this is quite effective, and because there is no direct contact, and people in the past who are really interested in the photography, they would remember that when we used to develop camera black and white films, there was a negative, and on which we export, and through which we would send light, and then we get the final image on a positive paper. And it's exactly the same basic concept which the projection optics methodology use. Only instead of on a paper, we transfer the pattern from the mask to a semiconductor wafer. That's the basic difference, but the overall principle remains the same. And when we speak of the projection optic methods, we need to remember a couple of critical parameters. One is the resolution, and which is K1 into lambda by numerical aperture Na, which is this is defined by the Rayleigh criteria invented by Lord Rayleigh. And this resolution is basically defines the critical dimension or the minimum feature size on a chip of a device. And the other parameter is the depth of focus, which is K2 and lambda by Na squared. Lambda here is the wavelength of the incoming light, and this depth of focus defines the range, basically the focal range for which the sharp image can be formed, because it's essentially an imaging system, where the depth of focus defines the range of distance on which the wafer has to be in the focal, basically the focal range of the projection optics. K1 and K2 are basically the process, these are constants, these are based on the processes. The important factor also, along with the wavelength of light, is the numerical aperture. It's basically when we say the numerical aperture of any optical systems, typically what it means is the light capturing capacity of the optical system. And uh, be it a reflective system, which uses a lot of mirrors, or a transmission system, which uses a lot of lens, it's essentially the numerical aperture is defines the light capturing capacity, and also how far, what kind of feature the imaging system can resolve. And these and when we one another point on this one is when we speak of the resolution of of the projection system in a uh, on a photoresist, is basically the XY resolution. It's along the X resolution, whereas the depth of focus is along the, if you take the plane of the photoresist at the XY, the depth of focus is along the Z direction. So basically, when we resolve the challenge here from these equations, what we get, that it is very good if you reduce, if you reduce the wavelength, the lambda, or increase the numerical aperture of the length, you can go to very low feature size. It can improve the resolution. But what you also do is also you reduce the depth of focus, and then it becomes really difficult to focus from sharp image. So these are kind of the self-contradictory requirements which play a very critical role when we design these photolithography systems. And then when we talk about the projection system, there is also two flavors: the stepper and the scanner. In the stepper, then what we see, I've talked about the mask. So basically, in a stepper, what we do is basically we expose the entire mask with the ultraviolet beam, and then we form the projection optics form an image of the entire mask pattern on a small area of the wafer. Why it is so? It's basically, you can imagine a 300 millimeter wafer cannot be exposed. Making such a huge mask or such a huge optical system is not really doesn't make is cost effective. So basically, the designing teams, what they did was to come up with a system where you expose the small area of the wafer using a complete mask. And the projection optics forms a very sharp image of this mask on the wafer. And then once you are done with exposing that part, you move to the next portion. And that's how you cover step by step, you cover the entire wafer, which is like 300 millimeter dimension. So this is what we call the stepper methodology of projection printing. What is a more evolved form of projection printing is known as a scanner. And as you can see, in a scanner, what we do is basically there is an annular beam of light which illuminates a section of the mask, the entire pattern of the mask which needs to be on the wafer is printed, and then we scan both the mask, and then we illuminate actually a small portion of the mask with a very small light. Why is it helpful? It's basically when we are talking about this, any kind of lithographic system, the light plays a very important role. The optics and the beam should be uniform, both spatially in terms of intensity and also its pattern. So it's very easier, technologically, it's much easier to bring this uniformity of the beam on a narrow area rather than a large, square or rectangular area. It's comparatively easier. And so what people do here is to make a small slit of light, which is uniform in intensity, uniform is in its distribution of light, and they expose only a smaller portion of the wafer. Then how do we, expose the entire wafer? Basically, this light is scanned across the mask, and or basically the mask is scanned across the light, so that the entire portion of the mask is exposed at one at a time. And then by that methodology, we can transfer the pattern to the wafer accordingly. What is does in reality also the wafer and the mask, they are moved at a very high speed against each other. They are separated by distance, but they move towards each other. And by that time, by that methodology, we can improve the speed of the scanning. We can improve the number of we can drastically reduce the cycle time of these exposure, and improve the throughput, which is essentially a very key important parameter in any industrial process, and it is wafers per hour. So in the past, in the previous slide, the scanning, when you see a scanner system, it looks a very simple, but what in effect it comes down to is this system, and this is basically an ASML DPUV scanner, DPUV being deep ultraviolet. And what you can imagine, what you can see is it's a very complicated system, and it kind of the size of this machine is basically of the size of a room, a pretty large room, and it has different components which have to work quite synchronously and quite in tandem with each other to make this to make the scanner work effectively in an industrial scale. So it consists of optical beam delivery systems. It consists of multitude sensors on the system, both optical and non-optical. It has mechanical and mechatronic modules. It has stages and other things. It has robotic systems to load and unload the wafers, and not to make it has electrical and electronic systems also to make sure that all these things have powered up. They can move with a certain speed. The light is generated to a certain frequency, and those kind of impacts. And to sum it up all, to make sure, as I mentioned, these are all automated systems. There is no human intervention when we run these machines. It has to have a huge software modules which can synchronize all this operation and make it more optimum through algorithms. And just to give you an as you can imagine, that it consists of multiple parts and things, but this is still not the most complicated of the systems which we make. There is a next generation system which we call the UV, which I will again explain later. And it typically an UV machine, just to give you a snapshot, highlight how complicated these machines can be. It consists of more than around 100,000 parts just to make this, which is make machine work. And so, as you can imagine, machines are really complex, and it involves a multiple kind of domain expertise to make these machines bring to life. This slides, I kind of overview of the how the litho tool evolved within ASML, and from what you see is from 1984, which we made the past systems, which we made, the resolution was roughly around larger than 1 micron, and to over the period, the resolution went down, like from 1 micron to 500, less than 500 nanometers. Then it comes to 90 nanometers in 1990s, up to 32 nanometers in 2000s, and then in 2010 we came with another bunch of another UV platform for our machines, where the resolution was less than 20 nanometers. There is another important parameter which is also shown here. It's called overlay. Now, what is overlay? It's basically when we say layer to layer accuracy. If you remember in the past, one of the images I showed, that there are multiple layers within the semiconductor chip. Like there is an area which is, for example, has a dopant area, and then the next layer on the top of that, maybe you put a metal layer. Now, when you first maybe do a percent of processes where you only have the dopants done, then you have to come back to the next set of processes where you have to define areas for the next step, which is, for example, the metallization process. Now, the metallization has to happen at the dopant area. So basically, the next process has to align with the previous process to a very high level of accuracy. And this is what we called overlay. And what we call overlay. And as you can see, as we have gone for less and less resolution, the overlay also has to be much higher the accuracy has to be much higher. For example, when we talking about resolutions to 32 nanometers, the overlay has to be the accurate less than to approximately 3 nanometers. When we talk about less than 20 nanometers of lateral resolution, the layer to layer accuracy has to be less than approximately 2 nanometer. And last but not the least, all of these machines are driven with high throughput, which means larger number of wafers, higher number of wafers per hour. I want to also highlight on this here that the semiconductor. It is not that once we come, once a semiconductor manufacturing company uses a particular machine, they phase out the uh, older ones. It's not always. It is not like that. Even today, the older, these older systems like PAS and systems are still used heavily by our customers who make the semiconductor, because depending on the type of layer, because when we talk about semiconductor chip, it is not the always of the, even the high end ones, they don't only use the lowest resolution for all their chip definitions. They use the lower one, they use a more looser specification machines, the larger footprints, and also the one or two layers can also be a very high critical dimension. So the use of the machine, the all this depends also what kind of feature size we want to do, and even the most modern chips may use the very old machines to make the patterns the way it is. Just as a highlight. Now, as you saw that when we moved from in the past previous slide that I showed that we went from a lower, uh, system with lower laser resolution to a much more higher resolution systems. How, what is a critical factor which make this happen? One of them is one of the most critical factors for this to happen, to that we can make chips from a lower resolution to a higher resolution, is basically the optics of the system. Like for example, what you see here is typically in photolithography systems, we use the ultraviolet rays because those are the, they have a very small wavelength and compared to the visible rays, and also it depends on the photosensitivity of the photoresist. So basically, they react to ultraviolet rays. But as we went, as we wanted to achieve lower and lower resolution, we had to move. The industry had to move from higher wavelength ultraviolet to much more lower wavelength ultraviolet. Like it started with 456 nanometers, then 405 nanometers, then 365 nanometers, and then 248 nanometers wavelengths. So basically, the optical wavelength played a very critical role as we move from the larger feature size to the smaller feature size. And why is it so? Basically, yeah, it's explained by the equation which I gave in the past, which is resolution is equal to k1 into lambda by numerical aperture. So even if you keep the same optics, the numerical aperture basically in a rough way goes with the diameter. Even if the numerical aperture is the same, the lower wavelength means lower feature size, so higher resolution. And what you see in the figure below is basically these are the wavelengths have been used for multiple. As we as we go down in the feature size, the industry moved to different wavelengths over a period of time. Like initially, there were 365 nanometer, which used a broadband Mercury vapor lamp. Then we moved to 248 nanometer, which uses laser systems, and then we moved to 193, which this 248 nanometers could support resolutions on the features are like 250 nanometers, 180 nanometer, 130 nanometers. After which the systems which use 193 nanometers were used to make feature size, which is like 90 nanometers, 65 nanometers, 45 nanometers. And subsequently, when these shrinking down was not possible, people did still make smaller features than 45 nanometers using this deep ultraviolet systems like 22 nanometers or 16 nanometers. But there was a limit which was reached. And then people invested in much more lower wavelength, which is like the UV, extreme UV, how we call, which is near to, if you can see in the, the optical wavelength pattern, it is near to the X-rays, and that's how we came up with the latest dimensions of the chips. So when we move from a one system platform to another based on the wavelength, what it needs is basically what it requires is come up more than often a new light source design. So basically, the light source has to be new. For example, when we the older system, the deep ultraviolet, the older 365 nanometer system would depend on mercury vapor lamps. Whereas when we move to the 248 nanometers, it used laser systems which are operated at 248 nanometers, KRF lasers, and krypton fluoride lasers. And then when we move to 193 nanometers, it needed another type of laser, which is the argon fluoride lasers. So basically, the source had to be redesigned based on the requirement of the system. Then we have to, explore materials which have high transmission or reflection efficiency in this optical wavelength. For example, the same optics cannot be optical. When we say optics, it's lens, mirrors. So the same optics which operates at for example, 365 nanometer may not give you the transmission at all, if at all, or a very low transmission at 193 nanometers. So basically, you have to come up with new materials to design these optics and clear on the aberrations and making sure the image is right. Then as we go down, the surface finish of this optics also becomes very critical, because when we typically talk about surface finishes, it's wavelength by 10, lambda by 10, that a surface, any optics when we make, for it to operate, for example, a lens to operate the way it is supposed to be, the surface finish has to be less than lambda by 10. So as we go down on the wavelength, the requirements for surface finish also goes up high, if you can imagine. And also these optical systems has to be precisely aligned. And typically we do mechanical alignment can be done up to the order of microns, but anything below that, it has to be done with actuations or calibrations. And when we are working with the systems, they over a period of time tend to be thermal, they heats up and they expand, and the focusing properties might change. So these things has to be compensated for when we are making the systems, and that has to be part of the design. Also, it requires a very high grade of cleanliness because of the sensitivity of these parts. Then some of the times the systems has to be, as I will explain a bit later, vacuum compatible, because that poses additional new challenges when we make this optical systems, because if it needs to be vacuum compatible, like it needs to be made of materials or holders which should not outgas, because that would destroy the vacuum. So these kind of precautions you have to take in design, manufacture, and also installation of these optical systems. Yeah, on the left, what I show here is for the deep UV photolithography optics. So here, this is again one of the past scanners which we used. And here what you see here is basically the overall schematic of how the light pass, start from its start to how it reaches the wafer side in the photolithography equipment. So here at the top, we start with a laser source. This is for the 248 scanner. So basically, it uses a laser source, and from the laser source, what we get a beam, which is a Gaussian shaped beam, means that it has a normal distribution curve, which we get a very narrow beam. And once the beam comes, it has to go through a beam expander optics, so that we have a reasonable size of the beam to start with. Then it goes through a beam transport system, which kind of are typically mirrors or beam splitters, which has to be aligned in a certain way so that the light is coupled from the this laser source. And just to remind, this is not part of the the overall lithography system, but the laser source might be downstairs in one of the other rooms, and from the laser source the light has to be coupled to the scanner, and but there is a bunch of optics which does that, mostly mirrors, where we, and also it has to be bended based on the how the the fab is designed. And when we do in the within, once it reaches the lithography, the path of the beam is going up. It goes through a bunch of optics. One thing is, for example, the pupil shaping optics. What it does is basically it has a couple of blades which kind of makes the shape of the beam uniform, and make sure that the beam is of a certain shape. Then it goes through the energy sensor, which kind of measures the intensity and ensures that that the intensity of the beam is of the right order, and also there is no deviation on the beam position, so that it can, and using the feedback from the energy sensors, the laser source has to be tuned. After that, then the beam goes through an integrated rod where it homogenizes the beam, and uh, then next it goes through a REMA, which is a reticle mask. Basically, when we call a reticle and a mask, it's kind of, in a modern world, it is defined in the same sense. So basically, what in the system, what it does is basically there are a kind of bunch of blades which kind of form a narrow, which helps to form the narrow slit which I spoke of in the past. On the So initially we have a larger beam, and from there we form a very narrow slit using this REMA entrance group. And from this narrow slit, this is then imaged onto the mask through a set of lenses, which we call reticle mask lenses. And then this is how we get an uniform beam, or a uniform illumination of the mask on the reticle. And after this, there is this, the mask being illuminated uniformly. Then we have a bunch of additional optics, which is called the projection lens, which kind of images the mask onto the wafer. So this is how, finally we get a mask pattern onto the wafer, and it depends very much on how it, the criticality of the image, the how good quality of the image is very much dependent on the illumination and the quality of the optics which we use, and also the quality of the source. And trust me when I say that each of these, individual modules, the people shipping optics and the integrated rod or the REMA lens, this needs a team of engineers to come up with them, because they're really precise and complicated system. Just to give you an idea, yeah, this is on the right side. If you see a projection optics for a DPV system, it is, the height of this optics is around 1.2 meters, which is almost like 3 feet, like a human thing. And it contains a bunch of lenses, which has to be really well maintained, which has to be thermally stable, which has to really maintain the sharp focus of different beam patterns. And that's why it's so critical. When we go over the UV optics, then what we see here is basically that when we started with the UV lithography optics, the one of the major challenge is we cannot use the same design concepts which we have used for the deep UV ones, because one of the main challenges in UV, which is typically 13.5 nanometer, it's highly absorbed by all the materials, and which we know, optical materials or any, and it needs a vacuum for its optimal to propagate. Otherwise, any material will absorb. So what it does for as a challenge is basically, from a transmission system which uses lenses, the system has to be designed, the same system has to be designed in a reflection based system. And this is what is shown, kind of a schematic of that. But here, the same functionality which I showed, the beam shaping, the illuminating the photomask, and also again the projecting the photomask onto the pattern, is done instead of lenses usage. We use it a bunch of mirrors to do this, and these mirrors are again quite precise, quite delicate mirrors, and you don't have many manufacturer of these kind of optics globally. For us, Zeiss is our Carl Zeiss is our partners in this, and who help us manufacture this kind of precise mirrors. But making the UV mirrors was too challenging. It was one of the not one of the most critical ones. There was a bigger challenge to come up with a UV source. And in the past, I've mentioned that we used laser sources like 193 nanometers and 248 nanometers, but making a source for the EUV specifically was in itself a challenge. There was no source available when this project began 20 years back. And so basically, what ASML came up with coming up with a new source generation and how it is generated. It's quite interesting. And what 13.59 it's generated is by excitation and relaxation of electrons, and what it needs is a plasma generation to generate the source. So here, what on the left side is how we do that. How do we generate this plasma? On the left, we show a brief schematic. There is basically a droplet generator which actually generates very tiny tin droplets, molten tin droplets, and these are like 25 micrometer diameter, and they are ejected from a generator at a speed of 70 meters per second. And once they go down in their path, they are actually bombarded with high powered CO2 lasers first, which flattens this kind of this small bubbles of these droplets, and then they're subsequently again bombarded with another type of laser, Nd:YAG laser, which operates at 1 microns. And what this process does, this bombarding does to the electrons, is the tin molecules are ionized and they generate plasma. And once from an ionization state, when they relax back, they generate this 13.5 nanometer, which are actually used as a source for these UV scanners that I spoke of. And yeah, the process is really complicated and it's quite interesting, also quite challenging. Here we use the CO2 lasers, which generate like 40 to 50 kilowatts of power. And yeah, it's and ASML invested quite a lot of time and energy and in conjunction with our partners. And it was almost a development period of 20 years till they came up with this kind of machine, which can do projection lithography on UV systems. Yeah, so far I did speak about the optics, but there are other, as much as optics does play a very critical role, there are other systems which also play a very critical role in the in making the high throughput of the wafers, and one of them being the wafer stages. And before I go into this one, I would go into the life cycle of a cycle in a twin scan. When we say a twin scan is basically what we do here is, before we expose the wafer, we have to measure the topology of the wafer to ensure that the exposure is at the right amount and the right energy at the right position. And so what to do is we need to measure the wafer topography. In the past, it was done in a sequential way where we measure the topography first and then we expose the wafer according to that, based on that information. But in the modern world, what we do, and specifically in the twin scan platform, what we do is to we measure one wafer in parallel, whereas we expose the other one. So this has actually enhanced the throughput time, but it also makes the process very complex and challenging. So what we do is, here we load the wafer, then we map the topography. Then once we enter the once the topography is mapped, we kind of expose the wafer in a sequential way. And once the exposure is done, then the kind of wafer is unloaded from the chamber and a new wafer is loaded. And when I say the twin scan, how this dual platform is what the twin scan does, and how it's enabled is basically this dual stage configuration, which has resulted in throughput. And we use here, the wafer loading and unloading is done using a robotic arm. The wafer stages, what we speak about, on which the wafer is loaded, they move with acceleration speed up to 5g, and which is like when you speak of a jet fighter takeoff, that's the acceleration they go through. And these are the stages which go through that kind of rigorous movements. These stages enable 6 degrees of freedom: x, y, z, theta, z, rho, pitch, or. And they're also coupled with very precise sensors. These are interferometric or encoder-based optical sensors for precise position measurement. And through this, combination of these technologies, what these wafer stages achieve is a position accuracy of nanometers. To be honest, I am not an expert on any of this in the mechanics and the mechatronics, but what I would definitely like to show you is a video, basically a cartoon on how these operate. It may take a while. So basically, on as I said, mentioned that on the one side you see the red laser, it's kind of topographing the wafer, where in the other way, it's kind of the other stage. It is being exposed simultaneously. Yeah, I would also try to give you a snapshot of the ASML-less machine. And yeah, this is on the left side, the latest machine which ASML delivered to its customers early last year. This is called the ASML EXS systems. If you can look at by the look of the system, you can imagine how big and how enormous the huge. It's like a monster in itself. And yeah, these are the people in the fab where, just to give a size comparison of these machines and how they're shipped and are installed. It's a 165-ton machine, and the cost it's quite high. It's approximately 380 million USD. One single machine costs this amount of uh, uh, money. Just to summarize my discussion, so basically, what I tried to give you an overview of the semiconductor manufacturing process from industrial point of view, and also try to explain the criticality of the semiconductor manufacturing to sustain the needs of modern life. I also went a bit deep into the photolithographic process and also some of the critical subsystems that makes the modern photolithography equipment possible. Future outlook. So the way I would like to complete it, that it's like, as you can industry, the semiconductor manufacturing, equipment manufacturing, it's itself a niche field, and it would be in demand, so for the future, so long we need modern chips. And this design and development requires quite active research of cross-functional nature. It's not isolated that somebody develops only the optical systems or somebody develops only the algorithms. It's a very closed loop things where different branches of basic science and engineering has to come together to make it work. It also needs a very active collaboration between academia and industry, and so ASML does that. We have a huge network with our industry globally, and it also for the aspiring, the new students who are graduating. It provides a very huge employment opportunities in terms of niche skill and new challenges if you want to explore them. These are some of the reference which I've used, and thanks to that. And I would like to end my presentation with a thank you for your patience and listening. And yeah, please shoot any questions if you like at this point of time. Thank you.
Dear participants, is there any query to our honorable speaker? Okay, then Shubhra ma'am, are you there?
Yes, sir. Yes.
Okay, okay, carry. Yes.
Okay. Thank you, sir. Thank you for the opportunity. And good evening, everyone. I am Shubhra Baroi. I am the Assistant HR at Abacus Institute of Engineering and Management. It's my privilege to extend a heartfelt vote of thanks at the conclusion of this insightful session. On behalf of the organizing team and all the participants of the Otol Faculty Development Program on Semiconductors, I express my sincere gratitude to our distinguished speaker, Mr. Sudha Sattva Ghosh, for sharing your invaluable knowledge and expertise with us. Sir, your deep insights into semiconductor manufacturing, optics, electronics and instrumentations gained through years of experience at leading R&D organizations and ASML have greatly enriched our understanding of this ever evolving field. The clarity with which you have explained complex concepts and their real world applications was truly commendable. Sir, once again, thank you for your time and for enlightening us with your expertise. We look forward to more such inspiring interactions in future. And I wish everyone a wonderful evening ahead. Thank you. Thank you, sir.